Welcome back to Differential Calculus. In this video, I want to talk about related rates problems. This is the kind of thing that we can just dive in and get our hands dirty, so let me get my head out of the way and we will do just that. In the first example here, I want to think about a conical hopper. All right, so we've got a cone. There is something in it that we're going to treat as a fluid. Let's say it's water. It's probably something a lot grosser than water, but we'll say it's water anyway. That seems like a reasonable choice on what to do. And there is a valve at the bottom of the cone, which is allowing water to leave. We know a couple of things about the cone. We know that the cone is 5 feet high and is 10 feet across. We know that the valve allows 0.75 cubic feet per minute to escape. And we know that at the time we are interested in, the water is 3 feet deep. All right. So we started off with a completely filled trough, or however it's going to be. You've got a circle on the top. It is shaped in a cone. There's a drain at the bottom. And we have quite a bit of information, honestly. We know how big the cone is. We know its diameter, but from there we can get the radius. We know its height. We know where we are. We know how deep the water is at the time we care about. We know how fast the water is escaping. And the question that I want to ask here is, how fast is the water level dropping? That is, the water is currently at this 3-foot depth. How quickly is that falling down? All right. So to answer that question, we are going to need to set up a couple of things. First of all, we have a cone, and we are talking about the stuff that is filling the cone, so that's volume. Volume of a cone is 1/3 times pi times r squared times h, where r is the radius of the cone and h is the height. I could use that to calculate how much volume is in the entire cone, but that's not what I want. I want to be thinking about what is happening to the water level, or whatever is in this cone. So the volume is constantly changing. I'm going to assume that the volume is implicitly a function of t. The radius is constantly changing. As the water level drops, the radius gets smaller and smaller. So the radius is a function of t, and of course the height is a function of t. I know that these things are going to be the case. Another thing that I know is from the geometry, the ratio of the radius to the height has to be constant. So that's something I can take advantage of, knowing this. The diameter of the machine itself, the diameter of the trough is 10 feet, which means that the radius is 5 feet. The height is also 5 feet. Because the radius and the height are equal at the start, if the tank were completely filled, the radius and the height will always be equal. That's an idea of similar figures, right? The cone that is filled with water is going to be similar to the entire cone. So we have similar figures going on, which is convenient because it will allow us to knock one of the variables out of the formula we're dealing with. And instead of all of that mess, we have simply that v of t is pi over 3 times h of t cubed. And with this setup, the time in question, I'll call T star. The volume at that time, I do not know. The height of the water at that time, I do know. It is 3 feet. I could use that to calculate what the volume is if I cared, but I don't think I need to care. So I'm just not going to worry about that. If it comes up later that I needed to care, then I will come back to that, but I don't think I need to. I also have this information. The water is leaving at 0.75 cubic feet per minute. That is the change in volume over time. That's V prime. And we are asked about the change in the water level. That's going to be H prime. That's the thing we need to solve for. That's the thing we're looking for. All right. And with that, I think it starts to become apparent why we called this a related rates problem. We are modeling a rate of change. The rate of change of the volume and the rate of change of the height are related to each other. We don't have an equation that involves the rate of change of either of those things, but we do have an equation that relates the measurement of those things together. And so that is going to give us our strategy. We can use calculus, we can use implicit differentiation to figure out how this equation relating this equation relating the quantities themselves will turn into another equation relating their rates of change. And that should be something we can solve. Right? As implicit differentiation goes, this one is pretty easy. The derivative of v is v prime. The derivative of h cubed is 3 times h squared, and then using the chain rule times the derivative, h prime. The 3's cancel each other out. And if I now suppress all of the of t's, because I don't actually care about t, I can write that v prime is pi times h squared times h prime. V prime I know is 0.75. Pi, well, 3.14, the circle constant, I know what that is. H is 3, that's being squared. Rearranging, that means that if I take 0.75 and I divide by pi and I divide by 3 squared, I get 0.02, that seems good enough. 0.027 is h prime. And I left myself a little bit of space because going back and looking at my units, my height was in feet, my change in volume was cubic feet per minute. So it makes sense that the change in height is going to have units of feet per minute. If you want to, you can multiply through by 12 to change that from feet per minute to inches per minute. It's 0.3, about a third of an inch each minute. You can multiply that by 60, again, if you really want to get that it's dropping by about 20 inches, 19 inches per second. You don't need to do any of that, but it might give you something a little bit easier to understand. Right? Seeing 0.027 feet per minute, I can't process what that speed looks like. If I convert that from feet per minute into inches per second, that suddenly turns into something that I can process. So for me, that's the sort of thing that is useful to understanding what's happening in this problem. But that's not what I was asked for. And what I was asked for is just to find the value. I'm going to use the units that we were talking about throughout the problem. This is how I would respond on an exam or something like that, 0.027 feet per minute. Right. The water draining from a conical tank is one of two canonical examples of related rates. Every calculus student does a problem involving water draining from a conical tank. The other problem that every calculus student looks at is the ladder problem. So in this scenario, I have a building. And I have a ladder which is leaning against the side of the building. I know that the ladder is 15 feet long. I know that someone is pulling the ladder from the bottom away from the building at 0.5 feet per second. And I know that at the moment I am watching this, the ladder itself is 8 feet above the ground where it's leaning on the building. I am not giving you the distance from the building to the bottom of the ladder, although you could figure it out from what I have here, and that might be useful. Oops. I wanted to do that in the other color. So, from basics of physics, we know that this ladder is going to be sliding down the side of the building. It's also going to be the case that it's not sliding down at the same rate it's sliding away. That's just not how things work. It is going to be sliding downward at a different rate of speed. And that's what I want you to think about. Right. Think about what kind of equations we can use to relate how things are happening. Again, I've given you the height, the distance from the ground to where the ladder is currently resting on the building. I've not given you the width, how far away from the building is the person who is pulling the ladder. You can calculate that. Using that calculation, using the formula that gets you there, you can also set up related rates in order to look at how fast the ladder is sliding along the ground and how fast the ladder is sliding along the side of the building. Great. So with those ideas in mind, I'd like you to spend a couple of minutes and see if you can put all of this together. Great. See what you can do with that one, and I will see you in the next video.